So I am Adnan Sharia. I am a PhD student in mechanical engineering, and my advisor is Dr. Arturo Montoya. So I will talk about the generation of periodic waves using Lagrange-plus-remap finite element method for evaluating the vulnerability of coastal bridges to extreme weather events. So the outline is first I will talk about the introduction. So piston type wave maker, first order wave theory, Lagrange-plus-remap finite element method, modeling numerical waveflow in Abaqus, results, and recommendation for numerical waveflow. So as I go through, you will have more understanding on this topic. So why we are doing this thing? So the main purpose of is to simulate the extreme weather condition effectively. In extreme weather event, you have sinusoidal waves. So we are trying to replicate the same behavior using numerical waveflow. And also, we want to make recommendation for numerical waveflow for the researchers who wants to do the same thing. So, for introduction, first I'll talk about the piston type wave maker. So, in experiment, people use this type of wave maker, which is very useful for shallow water waves. And you can see the piston paddle movement is a displacement zeta. So in experimentally, they move the paddle to replicate the wave or to create the wave. In numerically, we don't use the paddle. Instead of, we use the paddle velocity as an input. So as like an inlet boundary condition, this one, we use a velocity, which is a time derivative of this displacement to replicate the same wave. So to achieve the velocity profile, we are using the first order wave maker theory. So this is the U. So this velocity can be determined using this set of equations. This is quite complicated and it requires some nonlinear iteration. But the main thing is for a specific wave period, for a specific wave amplitude and a specific initial water depth, you can get this velocity profile using the three variables. So this is just an example. So this is the wave amplitude M, this distance, and this is the finite depth H, which is initial water height from bottom to rest water. So and then next I'll talk about the Lagrange-plus-remap finite element method. So this method is used in Abaqus to replicate fluid behavior. So this basically solves the Navier-Stokes equation in two steps. This is called operator splitting. So this is a bit detailed. I won't go through each of it, but it's just a numerical method. I'll just go through this diagram. So what it does, it deforms the mesh and then remaps it to replicate the wave behavior. So although it looks like the mesh does not move, but the wave moves through the mesh. Actually, the mesh deforms and gets remapped in every time step. So this is the very basic of this method. Now we talk about the modeling of numerical wave flume in Abaqus. So we use the initial water height, which is H. So at the beginning of the simulation, this whole region is filled with water, which is full, the blue region. The void region is red, which means there is no fluid. And there is WMR, which means the wave maker distance. We create this high mesh density region so that, in this region, there will be high velocity gradient. That's why we have NSB, which is called non-slip boundary condition. That's why it's high dense. And also within this region, there is also high velocity gradient. So we use very dense mesh. That is at the very top of it. So now I talk about the result and discussion. So I have used an example case study here. So I have used the initial water depth of 8 meter. Water height is 2.22 meter, which is basically the twice of the wave amplitude. And we have used wave period of 5.5 seconds. We have used a 800 meter long domain. And this is what the simulation looks like. At the bottom, you can see the results from Abaqus. And at the top, this is the results imported into MATLAB. So this is the same profile, just one in Abaqus and one in MATLAB. And this is the bounded region that I'm showing here. And the black line is the numerically predicted wave profile, and the blue is the generated wave profile. So from this, it can be seen that the deviation is quite low. It's not that much. So this is in previous case you have the time series, but it's difficult to understand. So I plotted it using time and x coordinate. So what does that mean? That you have the domain length here, which is from 0 to 800 meters along this way, and you have the time from 0 to 200 seconds. This is a zoomed in version of this region only. And the thing is, this is the first wave, which is actually propagating in this direction. This is the second wave, and this is the third wave. So how this graph is help us is actually it let us see the wave, I mean everything of the wave profile in one picture. So for example, we can see that the initial wave has dissipating behavior. It dissipates very fast. We can also see that there are some initial disturbances at the beginning. So this is x coordinate 0, which is at the inlet. And as you move forward, the wave progress, the dissipation, the initial disturbance dissipates and wave become more smooth, or have more smooth profile. So this is the top view of this image. So here I'll talk about the boundary effect. So what happened that this wave is actually, this is the inlet, this x equal to 0 line, this is the inlet. So your wave starts from here, and it propagates and hits the outlet boundary and reflects back. And when it reflects back, it just disrupts the incoming waves. And the more the wave is reflecting, the more it's getting disrupted. It's a constructive interference of the wave. And you can see that as you go in this direction, you have very high peaks of waves. You can also see it from this image. There are very high peaks at this region. So this region must be avoided when you do the simulation. So this is the boundary condition effect. I also worked with the stability. So I have used this region for first Fourier transform. So analytically, your wave should have 3 frequencies. These 3 frequencies is composed of. So I extracted the 3 frequencies for different x coordinates and find out the amplitude of it. And I can see that for all of these frequencies, the wave have some initial disturbance, as we think before, and it dissipates as it moves forward. So around 200 meters, wave has quite stable profile for this case. And now the recommendation for numerical wave flume. So people who want to design their own wave flume can use this information. So I have separated it into 3 regions. One is the region of instability, this region. So wave are quite unstable here. So you don't want to put your bridge in this location because of the instability. And then there is a region of wave dissipation. So this wave actually dissipates. So don't give that much good profile. And the next thing is the wave of disturbed, the region of disturbed waves. So this region is highly disturbed. It does not replicate the proper behavior of nature. So you want to exclude this region at any cost. So the suitable bridge location should be as close as possible to this line, which is the region of initial stability. I have chosen 200 meters from the inlet, which is this one. And also the limiting analysis time is 160 seconds, because after that you have the disturbed wave, so which you don't want. So if you place a bridge here with this 800-meter domain, you can analysis for 160 seconds. So, but if you want to increase the time, you may increase the domain length so that the wave takes more distance to reflect back. So yeah, so this is for recommendation, and then the conclusion. So in the conclusion, we have used the first order wave theory to generate periodic wave using the finite element method used in Abaqus. And the researcher can use this technique to replicate the wave. So the wave profile has good, match with the analytical result. And also the boundary condition is very important, as it causes the wave reflection, and it significantly disrupts the wave profile. And yeah, that's it. That's my presentation. So any questions? Thanks.
Thank you very much. And I really enjoy the video here on the importance of this modeling. Let me open the floor and see if people have questions in the audience.
Yeah.
I have a question.
Yes.
Well, I can see the computational cost of getting a better. I don't know if you could do this with a small, these small wireless sensors that we have. If we could collect some information and maybe send that and collect the simulation on real time or close to real time with your, I don't know the computational cost of doing this on time. I don't know if you could comment on that.
Okay, so yeah, that's a very good point actually. So look at the mesh. Yeah, so this is a very highly dense mesh. So okay, it's a bit complicated, but let me break it down. So if when you simulate only fluid, it requires very large time step. So you don't need that much time. But when you use structure along with fluid, the structure requires very small time step. So when I use the superstructure, the simulation can take actually weeks to compute. Just like let's say for 1 minute, it may take weeks for that. So what the best way to do is doing the mesh sensitivity analysis. So I have done it, but it's not finalized yet, and I didn't put it in the conference paper, so I didn't present it here.
With a are you talking about weeks with a supercomputer or with your desktop or your laptop?
In desktop, it takes like 2 weeks. In supercomputer, it takes. In our university, we use 4 processors. It takes around 1 week actually. Less than that, but close to that. It takes quite a bit of time.
Yeah, impressive. But but that's what it is. And any other question? Well, I have 2:57 on my time, and I think finished 3 minutes early, but I think that's okay. And people can join if they can take a half an hour break, and they can join the next session of the first day on session 4 at 3:30. So Crystal Metro and I want to thank all the speakers, and I think we have a very good session. We hope you enjoy the rest of the conference. Crystal, any other remark that we want to tell them?
No, I think that's it.
Great. Well, we thank you. We thank everyone.
Thank you.
Bye.
Thank you.